Good morning, everyone. I'm Xinpei Zhang. My topic is low precision quantization techniques for hardware implementation-friendly BERT models. This work is by me, Ding Minfei Yu, Xinyi Qiuqi, and Masahiro Futa. I'm presenter today, who is a third-year PhD student in the School of Engineering at the University of Tokyo. My research interests are in approximate circuit synthesis and neural network optimization. First, let me introduce some background. The transformer has shown a good performance in multiple fields, including CV and NLP tasks. The BERT is a leading deep learning model for NLP tasks, which is based on transformer. Models based on transformer also have some property that they always have a large amount of parameters. So, for example, standard BERT model, BERT base, contains 100 million of 32-bit floating point parameters. Which takes about 400 megabytes storage, which has heavy load, and the large amount of parameters using some 32-bit calculating is very heavy, also on the hardware implementation. And with the development of the transformer-based works, this amount of parameter can be 1 billion or larger, so it's very necessary to reduce the cost on storage and computation. So to reduce the storage and computation, the quantization would be very useful. And although there are some works already for the quantization, but there are only a few quantization works that designed aware of the hardware implementation. The main issue of this existing work is they're using a mixed data position in one model, that the precision transformation or hardware units with larger data type capability is necessary, so which causes an extra hardware complexity. Let's talk about the BERT. The BERT-based model contains 12 transformer layers and 1 embedding layer, which is dealing with the input. 1700% of the weights are in the transformer layer, and the weights in embedding layer has 3 types for 3 functions. Word embedding for word to vector, segment embedding to classify the word in which sentence, and position embedding just marks the position of the word. Recent work has found that if we avoid quantizing the position embedding, we can improve the performance of the model. However, if you do so, you are using some different precision in the embedding layer, which leads you to use some extra hardware units to deal with this situation. And activation is also a problem. So activation function here is in the feedforward part we can see in the figure. So we notice that there are some residual part in transformer layer, which means that you need to add the output of activation and weight together. So by this way, if we are using some different bit widths between activation and weight, we need to use some extra hardware to deal with this situation. And let's talk about the hardware resources we need for hardware implementation. So if we were using FPGA lookup table and SX to implement the BERT model, so the lookup table number and SQ error would become maybe 1/4 if we can reduce the bit width of the input to half. And if we're using some DSP as an expression of the calculation, if we can reduce the sum of the bit width under some limitation, we can parallel the calculation on the DSP to improve the hardware implementation. And on both of this situation, if we can achieve a lower bit width, we can reduce the need of storage, which is a benefit for hardware implementation. The basic idea of quantization is maps value in floating number into a smaller, lower bit width space to reduce storage and computation stress. The most strict way is some linear quantization with some scale factor determined by the range of the original floating number point and the bit width of the quantized space. So, however, the simple linear quantization may face some problems, which is that the distribution of the weights are not unique. which means that values nearing 0 have a higher possibility. And although the possibility is not very high, but it's also possible to come up with some extreme value. So if there is some extreme value, the rest of weights can only share in a very small space of quantization. By this way, a large amount of information will be lost, and the quantization quality will be dropped. And even if there's no extreme values, the most of the weights are sharing a very small space of quantization. So if we can solve this problem, we can also gain more information and improve the quality of the quantization. So our target is using clipping and two-piecewise method to solve such problem. Before that, let us introduce some related works. So there are already some works on quantization BERT models with some decent performance, except the QuantBERT, which is a very beginning research on quantization on BERT model. And actually, all the works has some clipping-like procedure to deal with clipping. However, no work has a nonlinear method solving the problem 2 we have mentioned in the previous slide. So aiming at only higher accuracy, but not aware of hardware, these works are sharing some different quantization bits, so which is not good for hardware implementation. First, which is a basic topic on QuantBERT. It is a very basic research with linear quantization and quantization-aware training. So in this work, the precision embedding is not quantized, and no clipping and linear mapping. No clipping is applied, and the mapping is linear. The scale factor Sx is derived from the input vector and absolute scale of the quantized value range. Although it's called QuantBERT, but if we change the m in the equation here, this work can be assigned with different bitways. Second is KD or QBERT. KD stands for the knowledge distillation, which is used to improve the performance of the model, which have 1% of the results improvement on the results. And in this work, the precision embedding is also not quantized and different from the linear quantization in the QuantBERT, which is using the absolute value to get the scale factor. In the KDL squared, they use LSQ, learn step quantization, to learn the scale factor to determine the quantization scale. So in this way, they can further improve the performance of the model. And for smaller bitways, here comes a TernaryBert, which is still using knowledge distillation and still do not quantize position embedding. In this case, the space of value is limited to -1, 0, and 1, so which means that the space of representation is only minus scale factor 0 and the scale factor. So for this, the calculation of the scale factor S is become very crucial. So they're using some optimization algorithm to optimize the scale factor to get a minimum distance of the quantized value and the original value. Or they using some they optimize the scale factor to get a smallest training loss. By this way, they can improve their results. Those are quantization works on BERT model, but there are also some data structure to improve the performance of the model, which is co-designed with hardware and software. The Microsoft floating point is such a data structure. The principle of the floating point from Microsoft is binding weights together with some shared exponents. Here is an example. In MSFP 12, with a bounding box equals 16, we use 16 numbers sharing one 8-bit exponent and using individual 1-bit sign and 3-bit matrices. The advantage of the method is because the design of the data structure, the dot product with such data structure is simplified. So in this figure, with two vectors with different shared exponential and individual matrices, dot product can be present here, which leads as a result. We just need to add the exponential together and times rest of the matrix. We can get the result of the dot product, and it can be actuated by the structure in this figure. Okay, now let's introduce our proposed method. So for hardware implementation, if always is quantized to the same precision, the structure can be simpler. And if we can, we also want some flexible bitweight activation, which may also affect the cost on computation on hardware. And we're using clipping and quantization on different weight combination to get such quantized BERT model. First is clipping. The basic idea of clipping is set values over clipping position to a clipping position. For example, here, if we set clipping position to 20, so we can see that there's some value which is larger than the clipping position. We just set them to a clipping position. By this way, we can see that we can use all of the quantized space and get a good quality of quantization. So we can see that the clipping position is very crucial for the clipping method. So our method is we have some list of candidate clipping position, and we select one with the smallest mean square error from the quantized value and previous value. And the second method we use is two-piecewise. After using two-piecewise, we can map the most of the value in a small area into a larger area. So let's have an example. If some original value is exceed some threshold, we just using a different coefficient to map that value. And if they're in the it's smaller than the threshold, we use another coefficient. So by this way, you can give the large amount of the value a larger space on the quantized space. So because so we can see that the threshold is very crucial for two-piecewise method. So we're using a similar method in the previous slide. So we have some candidates, and we choose the threshold which can minimize the mean square error from the quantized value and the previous value. Next step, let's introduce how our experiment is applied. So our code is modified from the Hugging Face transformer package, which contains a basic Quantized model. And based on that model, we introduce clipping and two-piecewise, and that is our work. And the results of the proposed method is an average result from 5 executions with different seeds. However, the transformer-based model is very sensitive to the seed, so that because we are using average value, so if compared with those using the maximum value, there will be 1% or 2% drop in the accuracy. And results of this other work is from their paper. So So if the baseline of the results is not the same, which means that the method of getting data may be different. This is experimental results of our work and other works. We compared our work with original BERT, Quantized, KDLSQ BERT, and TernaryBert, and Microsoft Flow Pinpoint. And the quantization means that how many weights are quantized. If the full quantization means that all the weights are quantized, and the partial quantization means that the position embedding is not quantized. You can see that for our method, if we're using full quantization for 4 bits on weight and 8 bits for quantization, we can have a good result that the loss on accuracy is not very large compared with the original BERT model. Further, we can further reduce the bit weight on activation. So by this way, we can further reduce the lookup table usage area of the circuit, and we can see that Besides the cola, which in our further experiments very sensitive to the bit width, other 3 benchmarks also have a good result. And as for our method, even if we can go to 3-bit on weight and 8-bit for activation, the accuracy on MRP CRT and STSP are relatively good. However, we can not get a good result on cola. And further, we tried full quantization and 4 bits on weight and 4 bit on quantization. You can see that on MRPC the loss is very small. However, we are using a full quantization with 4 bits weight and 4-bit activation, which means that it's very friendly to hardware implementation, and we can still get a good result with not a very large loss in accuracy. After the total experimental results, we also did some ablation study. So to try and find that which in clipping and 2-piece switch, which would be the most key factor of our proposed method, we can see that if the bit width is very large, for example for 8 bits, both clipping and the 2-piece wise can improve the performance of model. And using both of the methods can be also improve the performance of model at least in 6 bits. However, with the bit width become smaller, we can see that we cannot have a large space for 2-piece wise. And for example, if you're using 2 bits as a bit width, so we have no space for 2-piece wise quantization. So which means that so with a smaller bit width, so the clipping becomes a key issue and the leading point of the quantization of our method. Here, let me have a conclusion of my work. So we have proposed a method using clipping and 2-piece wise method to quantize BERT model, so achieving full weight quantization and lower quantization bit width in activation. So experiment results show that with full bit quantization, we can have about 86 to 98% of the baseline for glue benchmark expect cola. And we also showed that our work has flexibility with full quantization and low precision activation, which is very friendly for hardware implementation. Finally, if you have some questions or suggestions, please contact me. So this is my contact information. Thank you for listening.